Hello, and on behalf of OLI, I'd like to thank you for taking the time of your busy schedule to watch this video. Today, I wanted to show you a really new cool feature that we've developed at OLI, which is called the App Builder. The App Builder is a tool that allows you to access a flow sheet on the cloud. So you don't have to take the flow sheet with you on your computer. You could simply go to a browser and access it through there. So to start out with, we can start with opening a file here. In this case, I have a hydrotrudy scaling and corrosion example that I'd like you to look at. And you'll see it's simply the reactor effluent feeds going to the feed effluent exchangers, then getting a wash water treatment, and then the react. It's a simple process. And all we're doing here is we're tracking the amount of salts that form at the feed effluent exchanger and seeing if our wash water is optimized enough that we're dissolving all the salts that may form at the react. So if I wanted to take this to the cloud, I would go and click on File and go to Upload to the OLI Cloud and click on that. At that point, I would have to enter my username and password, and I could select the channel, make some comments, and upload this to the cloud. So once we click on Upload and the flow sheet is uploaded to the cloud, then we can access this flow sheet through our App Builder website. So for that, I'm going to bring over a browser. Okay, and in this case, as simply as typing appbuilder.olisystems.com. I have my username and password already saved, and I can click on Login. At this point, we'll be at the welcome page where I can access all of the channels that are available to me or that I am part of. So I can go to Ezekiel Private, and at that point, I can see that I have uploaded several cases, some in the draft format, some in the published format. The draft format will be uploaded once you click Upload to the OLI Cloud. And in this case, it's the hydrotreater scaling and corrosion example that I had shown you. So now I can click on Designer and go and start designing this application. So now that we're into the Designer phase, we can see that we've imported a diagram of the flow sheet. I'm going to make this a little smaller so that we can see it better and just zoom in a bit and see that we've imported the blocks, the streams that comprise that simulation. We can select the properties of the simulation, meaning inputs and outputs for the blocks, say the mixer. So let's look at this exchanger A and B. We can look at the input, temperature change and pressure, and this is related to how you set up that exchanger on the flow sheet, ESP application, and the output. Common outputs, heat duty, total inlet stream energy. If you wanted to look into that, we can look at utility streams if we had any streams, so that we can manipulate the duty of the exchanger as well. And we can also look at streams. So if you wanted to manipulate, how much inflow, say for example, the change, there was a change in H2S that was formed, or a change in HCl, or a change in ammonia. All these three drive the formation of the ammonium chloride or ammonium bisulfite salts, right? So you can put them into this section. So notice here, I'm going to collapse this for a bit now, and you'll see that I brought in quite a few things into the designer phase. We have the run button, that's to run the simulation on the cloud, but also I brought the group input, because if the composition of the stream that contains the contaminants changes, I want to be able to capture those changes, because that's what's going to change the salt formation. Now these numbers here that you see on these graphs, so we're tracking feed effluent salt formation potential and react salt formation potential. I'm going to go ahead and collapse this thing as well. And also the feed effluent exchangers temperature outlets. The numbers here are dummies, they're placeholders for the real numbers that we will see later on. So once you get to a point where you're happy on how your application is designed, you decide to publish it. Now the purpose of this application is to track feed effluent salt formation and react salt formation potentials to see which exchangers. So we have 6 shells here, but it's divided in A, B, C, D, and E, F, and 4 air coolers, A, B, and C, D. It's to identify which feed effluent exchangers will be at risk of salting out based on what we're bringing into the from the unit, from the reactors, and then if my wash water flow rate is enough to prevent ammonium chloride or bisulfite formation in the react. Okay, so once you're happy with it, we click on Publish, and I already have a published example, so we can go to that one. It looks exactly like that one. And I can go to my Scaling and Corrosion for Hydrotreaters application example, and then I click on New Run. Now that I'm in New Run, maybe I need a little bit more space to see everything, so I can click on F11 to bring in a full screen and make sure that I can see everything in there. And now I just want to see what this application does. All the values that are brought in from what was standard in the Flowsheet simulation that we used to upload. So I'm just going to click on Run and wait a few seconds for the results to come up. And what I'm looking for again is to understand what's the salting potential for my feed effluent exchangers, and do I have enough wash water flow rate for my react. So now that it's run, on the very top I see that at risk I have my exchangers E and F, the last ones in the heat exchanger train, that will be forming ammonium chloride salt. So this 0.628 is pounds an hour, as we can see here, pounds an hour of ammonium chloride that may form, and I don't have any ammonium chloride or any salts being formed in my react, which means my wash water flow rate is adequate. Now, this kind of question in a refinery, and this is a diesel hydrotreater, maybe I should have said that earlier, is asked constantly from the process team to the reliability team, where they're constantly asking, can I lower my wash water flow rate? Now you can create a tool and give it to operations, so the operations can answer that question themselves and really accelerate the time that you can make these decisions, especially in areas where water is scarce or it's a commodity, right? So for example, say that they want to try, okay, what if I lower the amount of wash water that I have by 2,500 pounds? So you have 5,000 pounds an hour coming in. Will that be enough? And they can do that themselves. And it's simple. All they got to do is change the wash water flow rate. You don't need to know electrolyte thermodynamics in order to extract value from this simulation. And yeah, 5,000 pounds an hour looks like it's still dissolving all of the salts that may potentially form at the react. On the right hand side, we have the feed effluent exchanger's temperature outlet. These are read from the simulation, okay? And these are set up, in these cases, are set up for delta T's, and so is in these cases, okay? Notice that there's a change in temperature here because at the inlet you also are adding some wash water and it's changing the temperature. And let's say that I want to just test, okay, well, how much water can I reduce before I start seeing salting out in the system? I can try now 4,000 pounds an hour. Okay, and run the simulation and wait to see if I'm going to get any salt. 4,000 pounds an hour is still good. What if I try 2,000 pounds an hour? Will that do anything to my system? Okay, and as I'm waiting and it's running, it looks like 2,000 pounds an hour is too little of a wash water flow rate, and I run the risk that at the inlet I will be forming salts in the react. Okay, what if I wanted to test, okay, what if I had no wash water? Where would the salts deposit? So let's just put 1 pound an hour and run the simulation. And as we wait, we'll see that all of the react exchangers will be forming salts. So now that we've done a couple of examples, let me just go back to the original one we had. I think it was 7,500 pounds an hour. Might have been a little bit less. Just humor me for a second. Because what I'd like to discuss now is what's the importance of having an application like this deployed into the field. So now you could, the process engineer or the reliability engineer that's designing or that was tasked with answering these questions on a weekly, monthly, or quarterly basis can design an application that can be deployed into the field for the operations and the process team at the refinery or the unit level to run these calculations themselves. And the design engineer becomes the custodian of the simulation. So as soon as there's new changes after a turnaround, or there's a new a new stream diverted into this unit, you can make those changes and adapt into the dashboard. In addition, you may get feedback from your operations and process team, and they say, okay, well, we know that we have water in our system, and we want to know what the water dew point is as we're coming out of the reactor. So if you have water and it starts to dissolve at the temperatures of EF, and EF already has salts that are going to be formed, those salts will get wet. And the piping ahead of the wash water injection port for the REAC could have wet salts causing corrosion, right? So you can make those changes on the fly and redeploy into the field so that operations and process teams can monitor these exchangers, answer those questions on the fly on a shift-by-shift basis or a couple hours basis, and continuously track the reliability of the unit so that you can extend the unit life through the turnaround. So now turnarounds used to be 4 to 5 years. Refineries now are trying to push 6, 7 years. And this tool gives you the ability to get to that point, because not only do you get to monitor for reliability, you get to exactly understand where the fouling happens in the feed effluent exchangers. And that's important because in the past, all we used to do is we used to take the unit down, or if you had a bypass, maybe you could bypass, but not everybody has a bypass set of exchangers that are sitting then idle until the other set fouls out. And so in the past, we'd have to bring the unit down, clean open every shell, clean them out. Some would be clean, some wouldn't. Put it back online, and it would take maybe 7 to 10 days of a turnaround, maybe 4 to 5 if your maintenance team was really well tuned to doing this kind of work. But now you can understand, okay, I need to, for example, focus on exchanger EF. I know those are the exchangers that will be having the salt deposits. So when I loosen up heat transfer, maybe I only have a temperature instrumentation at the inlet of AB and at the outlet of EF. When I lose enough heat transfer, I can do a targeted chemical injection at EF at a salt dispersant, clean out that shell, and get to my planned turnaround without having to take an unplanned outage. And that's absolutely powerful, because that is savings in the millions of dollars for a unit. So for example, a diesel hydrotreater of about 12 to 14,000 barrels a day, based on current market conditions, could save anywhere from $5 to $8 million depending on the length of the shutdown. Could save $5 to $8 million if they don't take an unplanned shutdown, and all they do is they do that chemical cleaning, targeted chemical cleaning to recover heat transfer and go all the way through their planned turnaround. And you can do this a couple of times through the life of that cycle. Yes, your chemical injection cleanings won't be as effective as the first one, but it'll allow you to get to that point without having to take that unplanned shutdown and lose the opportunity to make that money. So I hope you guys enjoyed this demo. It's been my pleasure to be here and show it to you. If you have any questions, please don't hesitate to reach OLI with any questions or concerns, or how you could apply these type of solutions to your industry. Thank you and have a great day.